Hello and welcome to Toddcast 34. Just a quick review. 33 involved a good amount of review of the terminology or overview of the terminology of nucleophile, electrophile, and leaving group, and then introduce the concept of how to make a good approximation of whether something's a good nucleophile or poor nucleophile, a good leaving group or bad leaving group. And so it's got the foundation. This podcast want to go more into the actual crux of how the reaction works. So I alluded to, in fact, we call it SN, substitution nucleophilic, and there's two versions, SN1 and SN2. This time I want to go into more detail of exactly what that means. And so we typically visualize nucleophiles, the atom carrying the lone pair, or the molecule that has the atom carrying the lone pair, coming and attacking electrophiles. So we draw an arrow from your nucleophile. So nucleophile, good Lewis base. Maybe it has a negative charge, maybe it doesn't. And then a carbon with a leaving group, and then whatever else is coming off the carbon here. We typically represent it as this lone pair comes in and forms a bond to carbon. The leaving group gets kicked out. The question we're going to run into is this first or second, the two arrows. Meaning, does it come in first and push its way on the carbon, forcing this off? Or does this happen first and then this comes in to replace it once it's already gone? That's going to be the difference between SN1 and SN2 in a nutshell. But before we get there, want to just emphasize a few other things. So charge alignment. So again, I've omitted, I probably should put them in, the other bonds coming off the carbon. Those other groups, poorly drawn, but just out of the way. It has a sneak in between the three substituents on that side, opposite of the leaving group. So negative is going to attract positive and repel negative. So this is what's known as backside attack. It comes in from the backside of the leaving group. One, there's more room there. A head-on collision with the leaving group won't knock the leaving group off. And number two, it's just good old-fashioned conservation of momentum. So what we mean by that, if you know anything, just basics of conservation of momentum in physics, the momentum of the system prior to a collision should equal the momentum of the system after the collision if no external force is acting on the system. At the molecular level, we're going to ignore the impact of any and all external forces and just say it's one atom colliding with a molecule or an atom in a one molecule colliding with another molecule. And so the momentum going in must be counted for in the momentum coming out. So the simplest picture, I'm going to say, let's say we have a nucleophile here. We have an electrophile with a leaving group. When this one comes in, it has a certain momentum. Once it collides, it's going to knock it out that way. The vector component is what matters most. So if this comes straight in, this group isn't going to go out that way or isn't going to go out that way. It's going to go straight out this way. That's conservation momentum. The momentum in must equal the momentum out, magnitude and vector-wise, direction and magnitude. So let me erase what I put in here. Have it come in. So there it goes. It comes in and knocks the other one out. So pretty straightforward. That's why they call it backside attack. So if the blue is on the right like it was, the red comes in from the left and knocks it out. If the blue would have been on the left, then the red would have come in on the right. So we refer to this as backside attack, which conserves the momentum. Momentum comes in left to right, it goes out left to right. The vector is moving in a straight line, parallel to the top and bottom of the page, perpendicular to the sides of the page, comes in, straight line, knocks the other one out, straight line. Okay. So backside attack, you're gonna hear that phrase often. The other thing I want to start with is I'm a firm believer that rather than trying to learn new material, learning something new, if you've treated something new, it's a challenge to absorb everything and get it down pat. And sometimes it's a little more painstaking than it should be. The best way to learn is actually take something you already know and make a correlation to it. So in other words, learn everything by analogy. I'm I say this constantly in my classes. You learn more science from kindergarten to third grade than any other 4 years of your life. All college does is take what you learn kindergarten to third grade and gives you more complicated definitions, some complicated equations, and some weird applications of it, but you already know it. This one you already know. So if you think of a situation where if there's a bench that can hold 4 people and there's already 4 people on it, you want to have a seat on that bench, you will consider the exact same things that a nucleophile considers when attacking a carbon in an SN1 or SN2 reaction. So, as I alluded to in the earlier slide, you have a decision to make if you're a nucleophile. Do you first push your way on and then knock the leaving group off, or do you wait patiently for the leaving group to leave and then you come in? So what happens first? The nucleophile coming in or the leaving group leaving? Now, the momentum picture I drew is in so-called SN2 scenario where the nucleophile first comes in and knocks the leaving group off. So that's one type, but we can't get to that point without first making a decision, which are we going to do? Come in first, push the other one off, or wait till it leaves, and then come in and take the space. So you want a seat on a bench that already has 4 people on it. Do you push your way on? So some of the decisions you're going to make. If you're going to push your way on or wait, things to consider beforehand. Amongst the things you want to consider, how crowded is it? Is it some really small people? Let's say it's a bunch of frail, small little children. Of course you're going to push your way on. Easy to do. They're small. If they're very bulky, then maybe it's going to be a little bit harder to push your way on. So you need to decide how crowded the bench is. How big are the people on the bench? How big are the groups on the carbon? Number 2, how much do you really want to sit down? So I'm sure you dealt with this situation on public transportation. You get on a bus, you get on a subway line, you get on something, and there's an open seat, and you know the just there's, for whatever reason, something in that environment that says, yeah, I think I'm just going to stand. You're not a very good sitophile. You don't want to sit down that much. Whereas another person gets on the train at the next stop and they just want a seat. They take that seat anyway. They wanted the seat more than you did. So there's certain situations where you have to decide how much you want to seat. So the other thing that's going to play a role is how good of a nucleophile or how good of a sitophile, how much does this person want to sit, will also decide whether they're going to force their way on or just wait. Is anybody leaving? So if anybody's leaving, they're going to leave and you're probably going to have a propensity to wait. Maybe not, but by the time you get there, they may have already left. And then peer pressure, the environment around you. It sounds sort of a strange thing to consider, but the solvent, the solution that it's in, and how much that influences the molecules plays a role. Your peer group, the people around you, the people influencing you, have an immediate sight line with you, have some stake in what you do. So generally speaking, this is kind of sequential. How crowded is it? How much you really want to sit? Somebody going to leave, and then peer pressure. Those are the before. If the people on the bench are really big, you're probably going to wait. If they're really small, you're going to slide in and push them out of the way. Pretty much how it works. Things to consider during the process. So if you were to push your way on, for a brief moment, there's going to be 5 people on the bench. If you wait till somebody leaves, then for a brief moment, there's going to be only 3 people on the bench. If you have 5 people on the bench, they're not going to rearrange, not going to move around. But if somebody leaves, then somebody at the end of the bench might move to the middle, highly unlikely, but it is possible. Or if somebody left from the end, then somebody in the middle seat is definitely going to slide over and take that preferred or better seat. So if there's only 3 people in there, they can move around. If there's 5, they're kind of stuck. They're going to be in a very predicted pattern at the end. The term monocheeking, it's, are you sitting all the way on the bench? If the bench can only hold 4 people and you try to squeeze 5 of them on there, like anything where you try to put too many people on, there's just not enough bench space. So you only are sitting down halfway. So you're affectionately known as monocheeking. When you have half your buttocks on the bench. So if there's 5 people on there, it's highly probable that 3 are on there and 2 others aren't fully on there. They're monocheeking. They're kind of on, kind of off. And so this is a scenario when the nucleophile is coming in, it's not fully on the carbon yet, but it's associated, it's near. When the leaving group's leaving, it's not completely on. It's now starting to break that bond. So you can say the nucleophile, when it comes on, goes through some phase of not being attached to monocheeking to finally being completely bonded. Leaving group goes from bonded to monocheeking to being completely dissociated. So if they leave first, then there's 3 people, they can move around. If you slide on, then 5 are on the bench, and a couple of them must be monocheeking. Okay, so they can move around. There's some monocheekers. Finally, in the end, afterwards, do you control your rate? So what impact do you have on how soon you sit down? And this is actually pretty huge. If you force your way on, then you control when you sit down. I'm going to sit down right now. So I'm going to push my way on and get my seat very, very fast. If you wait, you're at the mercy of when somebody leaves. Maybe they leave immediately, maybe they leave in 10 minutes. You're at their mercy. You have no control of when you sit down. So this is why we reviewed kinetics, is because if we study it and we find that if I change the concentration of the nucleophile, the rate changes. Nucleophile is affecting the rate, so the nucleophile must be pushing its way on. So that would end up being this case. It pushes its way on, makes 5 on the bench, and makes a faster reaction. So faster, and the rate depends on nucleophile. If you wait around, adding more nucleophile won't make any difference. You're still waiting for a leaving group to leave. If there are 5 people on the bench, then the order is very predictable, especially with conservation momentum. If you sit down on the left, you're going to squeeze people off and knock the person on the far right off. You know exactly who's falling off. You know the exact sequence of people on the bench afterwards. If somebody leaves first and you only have 3 on the bench, not so predictable. The spots are going to be different. So let's say there's you, and the bench is made up of people A, B, C, D. If you push your way on, D is going to fall off. So in the end, predictable positions be U, A, B, C. If you force your way on, you get a very predictable result. If, however, if let's say this person leaves, this person might move over and then you take that spot. Or this person moves over and that person moves over and you get that spot. So it will vary where you sit down based on how they move around. It is much faster to move your position on the bench. So B can slide over the C spot, C can slide over D spot much faster than you can move through the room and get to that bench to sit down. So rearrangement is much faster than nucleophilic attack. So we're going to learn the nuances of that because you can change seats really fast compared to how fast the person get in to sit down, the molecule will change its alignment most often to get people in their most comfortable seats. Hang on to that thought because that's going to become really important. Truth is, all these thoughts, all these common sense thoughts of dealing with a bench become key. So again, learn from an analogy and you'll learn it better. So if you understand how it works on a bench, you understand how it's going to work on a carbon. So the slower process is to wait around. The faster process where you influence the rate as a nucleophile is pushing them off. Okay, so the SN2 mechanism. The SN2, the 2 stands for 2 things involved in the rate determining step, meaning the rate of the reaction equals a constant, always does, depends on the solvent, the temperature, various other factors. It depends on the nucleophile concentration. Let me write that cleaner. And the electrophile concentration, both. So if I increase nucleophile, the rate gets faster. So the nucleophile comes into the backside, pushes the leaving off very slowly, and you make a new bond. So nucleophile lines up the electrophile because it has to be backside attack. So I've chosen cyano, a very good nucleophile, and bromine, a good leaving group. It has to come in from the backside. So this ball comes in, hits the big ball, knocks a small ball out. It has to come in linear fashion. So it is going to come in here. Those electrons are going to go off to bromine. Okay. Electron density is going to shift as it goes through this pathway. And so let me get rid of my yellow arrows. Trust the blue coming in and the blue leaving there. And I really should have this one starting not right at the carbon. It should be slightly offset from the carbon. So it looks better. Well, I guess I have it roughly the right spot, but it looks a little blurred in the picture. The dashed lines represent partial bonds. This bond hasn't fully been formed. This one hasn't fully broken. But when this comes in, it's going to crowd this side, and this CH3, CH2 has to move up and out of the way. The CH and the CH3 move out of the way. So these are now in the plane. So this is trigonal bipyramidal for the intermediate. There's 5 things attached, but the dashed lines represent partial bond, partially forming, partially breaking. So cyano and bromine, the nucleophile leaving group, are said to be monocheeking. They're only partially on the carbon, partially off the carbon. So where there are 5 things oriented around the central carbon, 3 are bonded and 2 are partially bonded. And then in the end, when the bromine leaves, the cyano group is on the opposite side. And you'll note, kind of like an umbrella, when the wind comes in, it turns inside out on itself. This was open and pointing to the left. Now it's open and pointing to the right. So we refer to that as inversion of the chiral center. It's a very predictable end result, but the carbon inverted. So if I were to do R and S assignments, priority 1, 2, 3, and 4 and back, so that'd be an R. In the end, priority 1 is a carbon with 3 bonds of nitrogen. I need to correct this picture. Oops. This is a little embarrassing. So this is 2, this is 3, that's 4. So in this case, I need to go back. I actually did my R incorrectly on the other side. I was looking ahead at my typo and worried about that. So the arrow is actually going from 1 to 2 to 3 counterclockwise. So it starts out at S. This one is 1 to 2 to 3. So it turns to R. So it inverts from S to R. And my apologies, I got so caught up in my typo here, lost focus. So just want to emphasize, it is coming in, backside attack, conservation momentum, goes through in transition state in which you have 3 real bonds and 2 partial bonds, 3 people on the bench, 2 monocheeking. Bond is forming, bond is breaking, and in the end, you have a new bond here. The bromine, or bromide in this case now, has been displaced. And all the substituents, the CH3, the H and CH3, started slightly to the left, finished slightly to the right. They have been inverted. So the chirality went from S to R. It doesn't always result in R to S or S to R, but it always has inversion. So what does that mean? How is that even possible? Well, if it ends up what you put on is a different priority. So if I put a group on here that suddenly isn't first priority. So if I substitute first priority for first priority, it has to go S to R, R to S. But every now and then you might go put in, displace a first priority to put on a second priority by the Ingold-Prelog rules. And in that case, then R to S and S to R wouldn't hold, but it still is inverted. It always turns it inside out on itself. Okay. It occurs in one concerted step. We use the word concerted. So if you've ever been to a concert is where everybody plays simultaneously, meaning the nucleophiles coming in and pushing the leaving group off at the same time. And the ethyl, the methyl, and the hydrogen are moving from slightly left to middle to slightly right. Everything is happening in concert. They're all doing it together. And again, it is a elastic collision where it comes in, energy is conserved, momentum is conserved. Comes in, knocks the group out on the other side. So visualize it just like that elastic collision we saw from the previous one. The conservation momentum, nucleophile came in from left, knocked the group out to the right. We typically write it that way, so I visualize it that way. In theory, who knows which way it's doing it in the actual solution, but for visualization purposes, comes in left, knocks the move out to the right. Okay, so a lot of information on this one. So want to be able to visualize this. And this is where, again, it might be a little on the tricky side, but here's my nucleophile and electrophile. So there's my electrophile, just like before, the 2-bromobutane, the nucleophile, the CN, and again, same top priorities, 1, 2, 3. So this is an S2-bromo. And as it comes in, I want to keep track of the energetics of it. So rehybridization, that's going to add some energy to the transition state. So it's going to start out in the beginning, and apparently it makes a better bond. Carbon-carbon bonds are stronger than carbon-bromine bonds. So the beginning with the bromine bond is not going to be as favorable as the end with the carbon-carbon bond. So step 1 or point 1 on the graph, not step 1, but point 1 on the graph is this starting region. Okay. Notice the CN started to move towards there. So we start to have it come in, and because these are now moving over, they're going to get a little more crowded. They're going to start getting too close to here, close to the bromine. It's going to have some repulsion. Also, this had a negative charge. That negative charge is now going to start being shared because it's giving part of its charge to here. We don't consider having a full negative. And bromide, which was neutral before, is starting to get electrons, so it has a partial negative. So notice this has a bigger delta. I'll draw this one bigger than this one. But that full negative on cyano group is starting to now turn into a little less than full, and you get a small hint of it. These groups are now starting to get a little more crowded, so it goes up in energy until it hits transition state. Transition state, again, trigonal bipyramidal. This is straight up, this is in the plane back, in the plane forward. So they are 120 degrees apart. This one and this one should have roughly the same size charge now. 0.3, the so-called transition state, where this is monocheeking, this is monocheeking. Transition state's going to shift. Again, notice now that the partial charges are equal. As this thing keeps pushing its way on, it's going to keep pushing the other group over. So now this is starting to push out a little less steric hindrance. This angle is getting a little bit bigger. So it goes a little bit down in energy. And you're forming a stronger bond than the one you're breaking until finally it pushes it off completely. And now it's a full negative on the bromine. And this is now these electrons are part of this bond completely. So in the end, you have your point down there. We now have a product and a leaving group. So that's your visual as it goes through it. It just turned inside out on itself. It literally pushed its way on and forced the other through 3 groups across. And so this is the product. So the same reaction I drew before. I apologize again for the typo, for having the wrong things there. This is how it's supposed to look. Hopefully that visual is one you can hang on to. It comes in from the backside, kicks out the bromine opposite side. So if it attacks on the left, knocks it out linearly to the right. Attacks on the right, it would knock it out to the left. So let's say this one was coming in, and that's coming off, this nucleophile, this is a reaction, then it would invert the other way. That is a pretty good summary of exactly what goes on. So here's our starting material. Here's our ending material, our product. And then we drew the transition state where you have 5 things attached, 2 monocheeking, 3 fully on. Okay, so what matters here? We're all the way back to that same bench analogy again. So consider before. Just like before, we made a decision, big or small, on the bench. What ends up, ethyl and methyl aren't the biggest R groups, but they're still bigger than H. So it's not clear. H is small, ethyl is kind of medium to big, CH3 is medium. So if something's small, medium, and it's starting to be a little bit large, not the easy decision. So the first story, crowded electrophile, how big are things on there? Can't make my decision. So the rule is this. If there's 2 H's on there, if it's primary, it's going to go by this pathway called SN2, where it depends on 2 things. It's going to come in and attack. If all 3 are R groups, R and R big groups, it's going to go by SN1. It's too crowded to force its way on. But when it's secondary, when this carbon has 2 R groups and an H, then it's going to be small enough somewhere on the H and CH3 side, so it might come in slightly lower, knock that out slightly up. so that I'm not 100% sure, so I need to consider a nucleophile. Well, it ends up, this is one of those five: amines, phosphines, cyano, deprotonated alkynes, and deprotonated sulfurs. So what solvent definitely matters, your pure pressure. If it's a hydrogen bonding solvent, it will hinder nucleophiles and they won't go as well. It slows it down. So it's kind of like all your entourage is clinging to you. But if it's an aprotic solvent, doesn't cling to it, it's free to move in, then it'll go by that matter, this pathway or faster. The transition state in the middle has 5 things attached. Again, 3 are fully on, 2 are monocheeking. Partial bonds, absolutely. Part way on, part way off. So your partial charges have to be considered. 2 people monocheeking. I probably like that phrase a little too much. Afterwards, inversion of chirality. Again, you went from an S center to an R center. Chiral inversion. And then fast or slow? Fast because you forced your way on, you didn't wait around. So it's a fast reaction. The rate depends on nucleophile and electrophile both, because the nucleophile is impacting it. So the rate for this one is some constant. Again, we don't know temperature, don't know the other factors, times Cn minus concentration times the 2-bromo butane concentration. So that is my nucleophile, that is my electrophile. Rate depends on both of them, which means we can do kinetic studies to figure out what type of reaction it is. So examples of how this works. I would look at this. My very first thing would be primary electrophile. That's telling me SN2 automatically. Good nucleophile. That's confirming SN2. So consider before, during, and after. So let me get rid of that. So crowded electrophile, not at all, primary. Good nucleophile, absolutely. So therefore, SN2 reaction. Afterwards, inversion. Inversion, yes, but chirality, not chiral. You didn't have an R and S to begin with, so you can't have any chiral inversion. The molecule did invert. These groups did move over so that they were on the left side. Now they're on the right side. But there was no change of chirality. So the molecule inverted on itself, but there was no chiral inversion. There's no chiral center change. Fast or slow? Fast because it's SN2. Okay, let's consider this next one. A little bit trickier in this case. Crowd electrophile? Well, electrophile, we have to look at where the leaving group is. So bromine, most common leaving group. That's what we decided is one of the big 5 that leave. So here's this carbon. It has 1, 2 other R groups. So crowd electrophile? Kind of. It's secondary. Hard to tell. So good nucleophile? Definitely. Another one of the big 5 nucleophiles. So methyl sulfide, good nucleophile, which means secondary can go either way. Methyl sulfide is going to make it an SN2 reaction. Inversion of chiral center? Absolutely, because this is chiral. You have a bromine, you have an H, you have a side of the chain without a methyl and side of the chain with methyl. So 1, 2, 3, H over here is 4. So you're starting at R, you will finish at S. So it has to come in. This has to come in from that side, which means whereas the bromine was up to begin with, SH3 is now down. Fast or slow? SN2 means it's going to be fast, but not as fast as the first one because of the crowdedness. So it's still a fast reaction because it's SN2, but your rate is, if it's a relative rate, it's not as fast as an uncrowded SN2. So a crowded SN2 will still go a little slower, but it won't be as slow as an SN1 reaction where you wait for the leaving group to leave. So this hopefully is catching on. We're making our decisions based on before, and then we're predicting the product based on what the mechanism does, so we understand what's happening after. Before and after. The bench analogy is really helpful if you understand what would happen in a bench scenario, you understand what's going to happen in a carbon scenario. 4 things attached, either way, both are the same example. So we've done the SN2 reaction. Future Toddcast will go into SN1, and then we'll look at the big picture of how they tie together. So hopefully this went well. And this is one of those things where it's starting to fall into place for you. So thanks for joining in, and I will see you at the next Toddcast. Bye.